Hello. Hello, everyone.
Hello.
If you can hear me, say aye.
Hi. Hello.
Okay, we are going to begin our today's lesson.
Hi.
Okay, I hope you are having a good evening. We're going to begin our today's lesson. Our today's lesson will be about a topic in linear algebra, which we normally use to solve power series problem in engineering mathematics. So the topic will be binomial theorem, and I'll be presenting. My name is Edwin korir. So the objectives of this lesson will be: one, we'll try to define by the formula binomial theorem. We'll also be able to understand the relationship between binomial theorem and the coefficients which form a triangular pattern, something we call Pascal's triangle. We will be able to recap on permutations and combinations, which are very useful theorems in binomial expansion. And we'll use an example to show how binomial theorem works. So straight away, we're going to look at this table on Pascal's triangle. So we are considering an equation A plus X. A plus X, when we expand, it remains A plus X. So the coefficient X now here is the variable. So the coefficient of X is 1 from our cell C5. Now, when we expand A plus X squared, when we expand A plus AX squared, we're going to get a number 1, and then 2x. So this one will be A squared plus 2x plus x squared. So the coefficient of A will be 1. The coefficient of x alone is 2. The coefficient of x squared will be 1. Now, if we are further to take another example, for example, A plus AX cubed, we'll be able to get 4 variables, each with coefficient 1, 3, 3, 1. So A, which will be A cubed plus 3AX plus 3x plus x cubed. Further, if you have to go to AX plus 4 cubed, the fourth square of it, we'll have how many? 5 variables. So we'll have A power 4, 4AX squared, 6AX. We will have 4x and x power 4. So we can see the pattern formed here is in form of a triangle. This triangle is called the Pascal's triangle. And these coefficients are very key when we are doing binomial expansion. So from the table, C1, C2 up to C9, from our table, they are coefficients of the expanded expression. These coefficients are very key in the performance of binomial expansions, and they are useful in performing mathematical operations of expansion using binomial theorem. So binomial theorem goes, if we have to do an expansion of, say, ax to the power of n, by binomial theorem, it goes that the expansion will be a power n plus n c1, that is the first coefficient, times an minus 1x plus, now n2, a n minus 2x squared will keep on. The next one will be n3 an minus 3x cubed up to nr an minus r x power r, and lastly n into n minus 1 a x power n minus 1 to xn. For example, a plus x power 20 will have a 20 combination 1 a power 19. This one in brackets are combinations, so combinations are written in this form. So we will have a 20 plus 20a, because 20 combination 1 is 20 factorial. So we're going to, from factorials, if we have n factorial, the n factorial will be n times n minus 1, the sum of its successive real numbers between 1 and the number. So, and it is read as factorial. 1 factorial is 1, 2 factorial is 1 times 2, all the way to 7 factorial is equal to 64. That will be 1 times 2 times 3, all the way to times 7. So, by convention, we also have factorial of 0 is 1. So, from the theorem, we'll have 20 factorial all over, 21 factorial, which is 1, times 20 minus 1, which is 19 factorial. 19 factorial will be 1 times 2 times 3. So 1 all the way to 19, from the 20 on top will be 1 to 19, and then 20 will remain. This goes on like this all the way. So the answer will be the successive series of A20 plus 20A19 from our formula, plus 190. That is the first coefficient of A is 1. A power 19, the coefficient is 20 all the way. So by proof, A plus x power n by binomial theorem goes from a number series from k to n. We'll have n combination k, x to the power of k, a n minus k. So when you expand a plus x, can you hear me? I hope you are following through. Yes? Hello?
Yes, we are following.
So we will see a plus x times a plus x all the way to the nth series. So a n minus 1 x power n is the number of terms in the sum which involves exactly Rx. So there are n minus r choices of Rx's from this combination nk. So n, and this is k, so that the coefficients of a, n minus r, if k is, for example, is 1, then we'll have and n is, say, 10 minus 1 x r 1, and the combination of 10 and 1. So we will have an example to highlight this. We'll expand ax squared. So ax squared will be a squared plus 2x plus x squared. So from the formula, replacing here, we will see we'll have a squared plus 2ax plus x squared. So the coefficient of a squared is 1. The coefficient of ax will be 2. X squared will be